Hello, thank you for coming to our presentation on intravenous white blood cell monitoring warning system. My name is Sam Mather, and I worked on this project with Cleo Cadwell, Stephen DeFreitas, and Mikael Hutterson. Currently, in the US, surgical site infection, or SSI, accounts for 9.5% of all healthcare-associated infections. While this number might seem low, if we take a look at low to middle income countries, surgical site infection accounts for nearly one-third of all post-operative patients. This large amount of cases not only brings harm to the patient, but costs hospitals an immense amount of money as longer hospital stays, revision surgery, and antibiotic rounds are needed to help treat SSI. To help solve the large amount of cases and slow response time, we need to take a look at how our body fights SSI. The way our body fights SSI is using white blood cells, specifically the neutrophils and macrophage found circulating in our bloodstream. The cells our group decided to focus on was neutrophils, as they are the most common white blood cell and are the first to arrive after an infection is detected. The image on the right depicts the steps of how neutrophils deal with bacteria, which is one of the leading causes of SSI.
Surgical site infections, or SSIs, are exactly what they sound like. They're infections that develop at the site where a patient has undergone a surgical procedure. They are classified by the surgical depth, which ranges from superficial infections to organ infections. During these infections, localized neutrophil levels greatly increase as the body acts to combat the foreign pathogen and prevent the infection from spreading throughout the body. However, a rise in neutrophil levels is also common occurrence in those who have just undergone surgery, as the body responds to a wound as it would any other. The difference here is that post-operative absolute neutrophil counts, or ANCs, show patterned behavior within the first week of surgery. Because SSIs can develop any time between the performance of the surgery and in some cases up to 90 days post-op, there is a period of time where the patient and physician both have limited knowledge regarding the presence of any surgical site infections. Most patients who experience SSIs show symptoms between 7 to 10 days post-op, where they could be charged upwards of $2,000 a day just to remain under the watch of the hospital staff. This slide shows some baseline values for pre-op and post-op patients, standards that are used to determine the presence of infection, and ANC trends and studies about this exact situation.
Our device is made to help track the amount of neutrophils in an area to see if SSI is present. To do this, our device has a silicone base layer with a glass case over the top to help protect the electrodes on the inside as well as the oscillator. The electrodes that we're using are in nanoporous gold, as it has a strong corrosion resistance, which was one of the major limitations of previous models. Our device will be attached to the vein using nitinol loops, which are loops used to anchor down devices found in the pulmonary artery. Next, our device contains an oscillator, which will produce a high-frequency signal that can be picked up outside of the body to help track the neutrophil count. Finally, our device is going to be coated in a hydrogel film reinforced with carboxymethyl dextrane coated Fe3O4 particles to help prevent platelet adhesion to our device.
Our implant will be coated in a hydrogel coating to inhibit platelet adhesion and counteract the formation of a thrombus. The implant will be coated in hydrogel made of 1% agarose that is 2 millimeters thick. Agarose has been shown to decrease platelet adhesion due to its high surface wettability and hydrophilicity, which is known to inhibit protein absorption and therefore platelet adhesion. Nanoparticles are also used in our hydrogel, as it's been shown that they are able to stabilize agarose.
We estimate the cost of production to range between $1,000 to $2,000, which stems from the list of charges below. Estimates were made for the cost of computer processing, glass casing, agarose-based hydrogel film, and nitinol loops, which each can vary depending on the manufacturer and the amount of devices being produced, but the total for these four pieces should be less than $1,000. The cost of operation for both the implant and removal should be around $4,000. This stems from the cost of a carotid endarterectomy surgery, which has a similar process while keeping in mind that the implantation surgery will be done in addition to another surgery. Our first competition is waiting for physical symptoms to develop. This is a current standard at hospitals, but the downside to this is that you are waiting for the infection to fully mature and develop before beginning any treatment, which can make the recovery process harder than we propose it can be. Our second competition are spit tests. These are also normally administered at the hospital. They can be useful for determining what type of infection the patient has, but is normally run only if the patient is showing signs of infection. Our third competition is the biofluidic chip. This device requires that blood be extracted from the body and run through the chip to determine if there is a higher than normal white blood cell count. The issue with this device is that it requires the patient to stay at the hospital. All three of these methods are normally done as a reactive process, meaning that the infection has gone through its incubation period and requires that the infection be fought off when already matured. The benefits to our device is that it is novel. We plan on creating the only device that is able to search and alert to the development of surgical site infections. Our device will allow for 24/7 monitoring of our patients while they are at home. In the chance that an infection develops, the device will alert the patient well before it becomes a problem and allow them time to get to the hospital for treatment. As a byproduct of our device, we plan on lowering the average duration of patients' stays at the hospital. This means that money can be saved from the cost of the very expensive hospital rooms, and also more hospital beds will be open in times where overcrowding of hospitals can be a large issue. Our device will be implanted during surgery, which will bring down the cost of the implantation and minimize the time and resources used. Finally, and most importantly, our device is proactive, which allows for treatment to begin well before the infection has time to finish its maturation process. The device will be implanted in a similar method that a stent would be. A small incision will be made and a balloon catheter will guide the device to its predetermined, most effective area. The balloon will then expand a nitinol loop and lock the device in place.
The sterilization method that our group decided to work with is gamma radiation. We chose gamma radiation as dry heat can degrade our silicone, which would have adverse effects when implanting into the body. We also chose gamma over ethylene oxide as we were worried about the ethylene oxide molecules getting trapped inside of our material, specifically our silicone, and having adverse effects when implanting into the body. After our device has been built and sterilized using gamma radiation, the hydrogel that we are applying to the top of our device will be applied in a clean room and in a full sterile environment.
In the pursuit of designing our device, there are certain engineering criteria that we need to meet in order to have our device perform to not only our standards, but also those of the national level. We need to ensure that our device can withstand the physical effects of being placed in the bloodstream. Our device must remain in place and resist the flow force that the circulatory system places on it, and must be able to withstand corrosion for the period of about 1 month, which is the period of time for which we estimate our device will be implanted within the patient. Our device must not pose a risk to the patient by remaining hemocompatible and avoid any cytotoxic tendencies. It must deter thrombogenesis and not impede the natural flow of the blood. From a functionality standpoint, it must also be able to detect the fluctuations of ANC levels within the patient to a reliable and accurate degree and ensure the count is accurate. Within the blood vessel, these are some interactions that are most notable. The processes that we want to especially monitor are the thrombogenesis and hemodynamics of the system, because those pose the greatest risk to the mortality of the patient. Monitoring the overall mechanical response of the environment and vascular walls are also of great importance because it will determine the degree of success that we can achieve in creating a well-anchored device. In accordance with ISO standards, these are the focal points for our testing criteria and the ways in which they will be accomplished.
In order to fully test our device, our group needs to focus on both biocompatibility and biomechanics. In order to test the biocompatibility of our device, we ran 3 different tests. We ran a cytotoxicity test to test if our device led to cell death, a corrosion test to see if our device and electrodes could survive the corrosive environment of blood, and a hemocompatibility test to see if our device would cause adverse effects on blood. The biomechanical tests our group would run would be a flow test and mechanical strain test to make sure our device could withstand the rate of blood flow and force inside of a vein. All of these tests we would conduct and run would be in accordance with the ISO standards and regulations.
For our animal models, we chose to use either canine or feline subjects for our small animal testing. They exhibit a similar blood flow rate to that of humans, which makes them great for testing regarding device translocation and degradation. Their immune systems function in a similar way to ours and would yield a great deal of information regarding cytotoxicity and hemocompatibility with a cost-effective source. In addition, there is existing literature and baselines found from studies regarding post-operative infections of these animals, which minimizes the use of these animals to find our own baselines. Our large animal model is the sheep. We chose to use this due to similar reasons for a small animal model. Sheep show similar blood flow rates and immune system functions, but now the anatomy is more similar to the scale that would be seen in the operating room. While we are hopeful about our device, there is always a balance between possible benefits and drawbacks. Our system would be instrumental in developing methods for early detection of wound infection and has a possibility to save lives by circumventing how individuals uniquely exhibit symptoms of infection and obtaining quantitative data about the patient's health. Patients would be able to return to their homes more quickly to recover in a more comfortable environment, save both the patient and hospital money by shortening their stay, and minimize any overuse of antibiotics in the recovery process. We are aware, however, of a couple drawbacks and limitations that we could face. First, because the device does go in, it has to at some point come out, once the patient has no more need of it. This begs the question, by performing a procedure to remove the device, there's an argument to be made that another device would just be used to monitor the new wound that creates an endless cycle of implant and explant surgeries. The hope here is that the disparity in the lesser severity of the minor wound from the explant procedure would outweigh the benefit that it provides in monitoring the recovery process for more large-scale procedures. Smaller incisions from the explant wound would have a much lower likelihood for infection than the preliminary surgery. Another worry is the variability in patients' reactions to surgery and the uniqueness that one's immune system has to different scenarios. Our goal is to combat this by obtaining data from patients prior to performing the procedures to get up-to-date information about any existing abnormal neutrophil levels that could skew device readings during the recovery process.
Thank you so much for your time, and we look forward to answering your questions.